Origin offers a complete statistical process control toolset which can be used to measure, monitor, and control the quality of a process. This video will focus on the first step under the SPC app. Identify the distribution that best fits the data on hand. Once we select the distribution for the data, we can use it to make real-world inferences, such as calculating control limits, predicting defects, and identifying process improvements. The rocket fuel tank pressure testing dataset includes 50 observations and 2 variables. The first variable, batch, is the production lot, and the second variable is the pressure at which the fuel tank failed. Pressure is measured in psi or pounds per square inch. The engineers are interested in making sure the fuel tanks will fail above the minimum required pressure. Under Statistics, Quality Improvement, click on Statistical Process Control. Click on the first tab, Identify Data Distribution. The measurement data are in column B, burst pressure. The subgroup size is in column A, batch. If you have an equal number of observations in each subgroup, you can also select constant, followed by the number of observations for each group. We won't do that here, since we already have a column for batch. Click on Distribution. Select 4. Let's select normal as our first option. Since the measurement data are all positive, the Box-Cox transformation is a good second option. For the last 2 options, let's select the Weibull and log-normal distributions, which are widely used in reliability analysis applications. Click on the Box-Cox tab and select Optimal Lambda. It is easier to look at lambda when it is rounded to the nearest decimal point. But you can choose to uncheck this box if you want to retain the original, calculated value of lambda. We can leave the default settings as is for the Yeo-Johnson and Johnson tabs since we did not select these transformations. Click on Create Probability Plot. Make sure all options are selected. You can sort distributions by the Anderson-Darling test statistic, where the results will be sorted by ascending AD value. Or you can sort by descending p-value. This option can be used to easily select the distributions that best fit the data. Let's select p-value. The Box-Cox lambda value is -1.5. A transformation of -1.5 is best used when there are right-skewed data. We chose to sort the goodness of fit test table by descending p-value. Following the Box-Cox transformation, we conduct an Anderson-Darling test to determine if the transformed data follow a normal distribution. The null hypothesis is that the transformed data follow a normal distribution. The displayed p-value is large, and we do not reject this null. For the log-normal and the normal, the null hypotheses are that the data follow a log-normal and normal distribution. Again, the p-values are large, and we do not reject the null. The null hypothesis for the last row is that the data follow a Weibull distribution. We reject this null hypothesis. The next table shows the estimates of the distribution parameters for the 3 distributions of interest, normal, log-normal, and Weibull, and the distribution following a Box-Cox transformation of the original data. Let's check the probability plots, which are also sorted in order of descending p-value. In the plots, we want to see data following a straight line, and this line remaining within the confidence bounds. The Weibull probability plot is the only plot that fails these 2 requirements. When choosing a final distribution, here are 3 things to keep in mind. Look at historical studies and similar applications in your field. Simpler is better. If a distribution with transformed data is selected like the Box-Cox transformation, keep in mind that if you want to make real-world interpretations, such as calculate a predicted value or a confidence interval, you will need to reverse the transformation back to the original units.